Hi, everybody. I'm Gail Wallace-Jack. I'm the president of CASIRIS, which is the Center for the Advanced Study of Religion and Science. And we are a support organization for Zygon Center and also for the Zygon Journal. We couple with the International Society for Science and Religion and IRAS, the International Institute for Religion and Science, to create this set. Now, tonight is a special situation because we're actually bringing you this setup from Lutheran School of Theology, which is another one of our co-hosts. And this lecture is part of our course for Zygon Center on the Epic of Creation. So we have a public portion of that, which is the first hour or so, and then we have a private portion when the students get the chance to take on Grace and ask her questions. So let me introduce our speaker for this evening. She is a familiar face for those of us at Zygon Center, where she's been lecturing for many years, and that's Grace Wolf-Chase. Grace is a senior scientist and senior education communication specialist with the Planetary Science Institute. She's also taught at Lutheran School of Theology in Chicago for many years in many of our different series. She's also vice president for CASIRIS, who is hosting this lecture. She got her AB in physics from Cornell, PhD in astronomy from the University of Arizona. She was awarded a National Research Council postdoctoral fellowship when she was at the NASA Ames Research Center. Then she went to University of California, received the President's Postdoctoral Fellowship at UC Riverside. She worked at the Adler Planetarium for many years before she joined the Planetary Science Institute. Tonight, Grace is going to talk to us about cosmic creation through the ages. We ask you to keep your questions to the end. When we're done, I'll have a call for questions, and you can either enter them in the chat or you can raise your hand and we will call upon you. With that, I'd like to turn it all over to Grace. Grace, please take it away.
Thank you so much, Gail. Let's see. Okay, so you should all now be able to see my screen, hopefully. Not in presentation mode. Okay, thumbs up. Thank you. Great. Okay, wonderful. So again, as Gail mentioned, I've been a speaker in the Epic of Creation series since the early 2000s, and thank you, Gail, for continuing to invite me back. I'd like to start with a quote by Sarah Maitland, where she says, "Natural history is not taught in seminary. This is curious, as most people in pastoral ministry are about 567 times more likely to be asked about cosmology or subnuclear physics or human biology or evolution than they are to be asked about irregular Greek verbs or the danger of the Patripassianist heresy." Well, I'm very happy to say that the Zygon Center has been offering science programs to seminary students for decades, and an increasing number of seminaries are integrating scientific content into their courses and their events. Now, most, if not all, of the scientific talks in this EPIC series are going to focus on planet Earth and its inhabitants. So it's my job to give you a taste of how Earth fits into the bigger cosmic picture. I've been a professional astronomer or astrophysicist, if you will, for more than 30 years. However, astronomy has been my lifelong passion. Inspired to a large degree by science fiction, and I'm unashamed to admit that the original Star Trek series in the late 1960s played a big part in that. So for my 16th birthday, my mother gave me the choice between a large party or a telescope, and you can see my choice in the upper left corner there. I studied the birth of stars, which is very closely connected to the birth of planets. And star formation has been going on since the universe was very young, and the processes of star and planet formation continue in the universe today. Whoops. So the space sciences now include many of the major branches of science that have been developed on Earth. Now, clearly, I can't begin to even scratch the surface of developments in all these fields in 1 hour, but I do want to make you aware of them. Even as these fields have become ever more specialized, they've also become more interdisciplinary and led to successively larger collaborations between scientists with complementary expertise. When I was in graduate school, people who identified as astronomers who studied space beyond our solar system, and those who identified as planetary scientists who studied everything within our solar system, rarely interacted. And that started to change once we started to accumulate evidence that stars and planets are actually born together and that many other stars out there have planets. So astronomy is an observational, as opposed to an experimental science, that uses telescopes and other instruments to collect information in the form of light, particles, and gravitational waves from distant objects in space. Today, we speak of multi-messenger astronomy. So we collect light across the electromagnetic spectrum, not just the small fraction that our eyes are sensitive to that we call visible light. We collect light in the form of radio waves, microwaves, infrared light, ultraviolet, X-rays, gamma rays. And many of these wavelengths actually don't make it through Earth's atmosphere, so we have to put at least some telescopes in space. Now, we also get information from high energy particles, bits of atoms like protons and electrons that arrive from energetic events that occur in space. Gravitational waves were predicted by Einstein's general theory of relativity in 1915, but only first recorded 100 years later in 2015. As science fiction-y as it sounds, gravitational waves are ripples in space-time, and we'll say a little bit more about that in a bit. So I'd like to take a look at the big cosmic picture before we get into the weeds, before we get into the details of how we've assembled this picture. The history of our universe begins about 13.8 billion years ago, when the universe was in a very hot, very dense state known as the Big Bang. If you compress the 13.8 billion year history of the universe into one Earth year, then one cosmic second is about 500 years. This big history is accessible to us at our point in time because of the finite speed of light and because we live in an expanding universe with a finite beginning. The implications are profound. We have a fossil record of the past that comes to us from very distant objects and enables us to explore how the universe and its contents have changed over time. And I want to note that on this cosmic calendar, our solar system doesn't even form until September of the cosmic year. Our sun is what we call a third generation star. The development of multicellular life on Earth doesn't occur until December, with the development of human civilization occurring in the last minute before midnight on December 31st. Modern science, as we practice it today, doesn't arise until the last second on this cosmic calendar, and a very long individual human lifetime spans about a fifth of a cosmic second. Now, here's a somewhat less Earth-centered way of looking at the history of the universe. The vertical extent of the grid in this graphic depicts the relative size of the universe through its history. The far left depicts the earliest moments we can now probe, when a period of inflation produced a burst of exponential growth of the universe. The afterglow light pattern, the afterglow microwave radiation, comes to us from a time when the universe first became transparent to light. It's been recorded by a number of telescopes that have observed patterns in this microwave background in ever greater detail. The light was emitted about 375,000 years after inflation and has traveled through the universe largely unimpeded since then. The conditions of earlier times are imprinted on this microwave background, and they set the stage for later developments of the universe, like the formation of stars and galaxies. For the next several billion years, the expansion of the universe gradually slowed as matter pulled on itself through gravity. More recently, the expansion has begun to speed up again as the repulsive effects of what we call dark energy have come to dominate the expansion. Now, the way the universe has been envisioned scientifically has had an impact on thinking about God. In Isaac Newton's time, the universe was envisioned something like a large mechanism, where space was envisioned to be an empty stage that provides an absolute frame of reference for the material cosmos. The material world behaves strictly in terms of causes and effects, and Isaac Newton envisioned gravity as a force acting at a distance between matter. Now, the mechanistic thinking of the universe gave rise to thinking about God as some kind of a cosmic engineer, and to what's known as God of the Gaps theology, where God as explanation competes with scientific explanations, making God's role smaller as our scientific understanding grows. Many people today still think about God in that way, although our way of thinking about the universe has changed considerably over the last century. So today, the universe seems to be better described as an interacting web of relationships rather than a collection of things. Two 20th century branches of physics revolutionized our understanding of the universe: quantum mechanics, which describes interactions at the level of atoms and subatomic particles, and general relativity, which describes interactions that govern the large-scale structure and evolution of the universe. More and more, we hear metaphors from biology, such as nature and nurture, that work very well in describing aspects of the physical world, such as in my field, the birth and evolution of stars and planets. So I'm not teaching quantum or general relativity tonight, worry not, but I'd like to briefly touch upon how they've been crucial to our current understanding of the universe. So in the early 20th century, Albert Einstein's development of general relativity brought with it a new understanding of gravity. Space and time are inseparable and not absolute. Isaac Asimov, Albert Einstein thought about gravity not in terms of invisible force, which to him was spooky action at a distance, but gravity is actually in the nature of space-time, which is like a fabric. It can stretch, bend, twist, and ripple. So space-time is dynamic and is warped by the presence of matter. In the words of physicist John Wheeler, space-time tells matter how to move, and in turn, matter tells space-time how to curve. One prediction of general relativity is that the universe should be expanding. Edwin Hubble, and over time, that should increase the distance between galaxies. Edwin Hubble, with the help of a janitor become astronomer's assistant named Milton Humason, is credited with the observations that illustrated this expansion. However, an interesting historical fact, although Hubble is credited for the discovery of the expansion of the universe in 1929, the Belgian priest, Georges Lemaitre, published a solution to Einstein's equations of general relativity for the case of an expanding universe in an obscure Belgian journal 2 years earlier. And when a translation of Lemaitre's paper appeared in 1931, the equations that describe what became known as Hubble's law had been removed. Lemaitre himself did this because he felt that his distance estimates to galaxies were not strong enough to validate his discovery. Lemaitre went on to propose that the logical consequences of an expanding universe implied an origin at a finite point in time, earning him the double entendre title, the father of the Big Bang. Now, Lemaitre was accused of having his deeply held religious beliefs lead him to the idea of a universe that had a beginning, and his response is very interesting. Lemaitre said, "As far as I can see, such a theory remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. For the believer, it removes any attempt at familiarity with God. It is consonant with Isaiah speaking of the hidden God, hidden even in the beginning of the universe." So Lemaitre's comment is a rejection of all types of God of the gaps theology. Now, it's important to realize that the Big Bang is not like an explosion that sends shrapnel through pre-existing space. Space and time, at least as we currently measure them, originate in the Big Bang. So by the late 19th century, astronomy became not just about how things move in space, but also about what they're made of, their composition, effectively turning astronomy into astrophysics. I want to introduce two people who did important work in this regard, but who probably aren't household names. Angelo Secchi was a Jesuit priest who, among many other contributions to science, built and used a spectroscope to study patterns of dark light in the spectra of different types of stars. So a spectroscope is an instrument that breaks light into its component colors. Now, Secchi observed these patterns of light and he realized that they were related to composition. However, at the time, there was no theoretical framework for understanding how the patterns are produced. In the 20th century, quantum mechanics could be applied to understanding them through the interactions of light and atoms. Cecilia Payne was able to relate stellar spectra to temperatures as well as compositions, and to determine that stars, including our sun, are mostly hydrogen. Now, her work was initially met with resistance, partly because hydrogen is so rare on Earth, but also because she was a woman in a very male-dominated field. A few years down the road, however, astronomer Otto Struve referred to her dissertation as the most brilliant PhD thesis ever written in astronomy. Now, towards the mid to late 20th century, as telescopes were built that could collect radio waves and infrared light, spectroscopy made possible the discovery of cold, dusty clouds in space that contain hundreds of molecules, including organic molecules made up of long chains of hydrogen and carbon atoms. One of the tasks of astrochemistry is determining how complex molecules form and evolve in space. And with the discovery of exotic forms of life in many harsh environments on Earth, biologists started collaborating with planetary scientists and astronomers to explore how life might be detected either in situ on other worlds in our solar system or through remote observations. So let's now take a quick tour into space to see how timescales and distances relate to each other, and to look at some of the contents of our universe. The moon is about 250,000 miles from the Earth. It takes light a little over a second to travel the distance between the Earth and the moon. And I actually remember when this photo was taken, when we got to see what our planet looks like from the moon, from space, for the very first time. Traveling further out to a larger scale, our solar system includes the sun and the various kinds of worlds that orbit it. This includes things like planets, dwarf planets, their moons, asteroids, comets, and other small objects. Now, on this scale, the speed of light starts to become very important in considering the transmission of information and communication. For example, the distance between the sun and the earth is roughly 93 million miles, and it takes light 8 minutes to traverse that distance. So we say the sun is 8 light minutes away. What that means is if there's a very big flare on the sun that occurs this instant, we don't know about it for 8 minutes. Now, traveling through the radius of the solar system, about 5 billion miles, it takes light not minutes, but hours to traverse that distance. If we go to even larger scales, our sun is a star, and stars come in different colors, temperatures, sizes, masses, brightness. This diagram shows you just a few of the different stars nearest the sun. On average, stars are separated by a few light years, where 1 light year is roughly 6 trillion miles. For most of their lives, I'm using air quotes here, stars are powered by nuclear reactions that fuse hydrogen into heavier elements at the enormous pressures and temperatures deep within their cores. About 70% of all the stars out there are stars that we call red dwarfs, which are intrinsically up to 100,000 times dimmer than our sun. So by intrinsically, I mean if you could line up a red dwarf and the sun at the same distance, they would be that much dimmer. Luminous blue stars, on the other hand, can be 100,000 times brighter than our sun, but they make up less than 1% of all the stars. These are stars that explode as what we call supernovae after millions of years, and they seed interstellar space with heavy elements. Although these stars are rare, they're essential to the development of life. Whereas the most luminous stars last only about 1 million years, they're kind of the gas guzzlers of the universe. Stars like our sun have lifetimes of about 10 billion years, and red dwarfs will be able to last trillions of years. So all red dwarfs that have formed since the beginning of the universe are still out there. With the exception of the lightest elements, most of the natural elements on the periodic table were produced in stars, and the heaviest natural elements were produced in supernovae explosions, where temperatures can reach several trillion degrees. It's also these explosions that distribute the elements produced during the star's lifetime. Without supernovae, heavy elements would be locked inside of dead stars. Hydrogen and helium were produced by the Big Bang, and very light elements such as lithium, beryllium, and boron nuclei are thought to come from cosmic rays, which are high-energy fragments of atoms that are produced in different types of cosmic events. So the sun, as well as all the other stars you see in the sky, and many more that you don't see, belong to an enormous group of stars we call the Milky Way galaxy. We infer the overall spiral shape of our galaxy by making measurements from our position in the galactic suburb, so to speak, about halfway out from the center of our galaxy. We can't take a picture of our galaxy. It takes light 100,000 years to traverse the diameter of our galaxy. So keep remembering that to look into space is to look back in time. We never capture now. And by the way, 100,000 light years corresponds to roughly 600 quadrillion miles. Now you'll note a dark lane through the Milky Way, as you can see it from a really dark sky location. That's not the absence of stars, but that's where cold clouds of gas and dust block light from stars in the plane of our galaxy. These clouds are where stars initially form, and although we can't see them, we can study them using infrared and radio telescopes. And the fuzzy pink patches you see here indicate stellar nurseries, where the most luminous newborn stars light up their environments. The nearest stellar nursery that harbors some of these really luminous stars is in the familiar winter constellation of Orion, called the Orion Nebula. And at a distance of about 1,400 light years, the Orion Nebula contains a large cluster of young stars. This is a Hubble Space Telescope image of the central part of the Orion Nebula. The gas is lit up by the brightest stars at the center. The dark foreground objects are roughly the size of our solar system. They've been studied in great detail during the past 3 decades, and we have a lot of evidence that these are forming planetary systems. We also have evidence that our solar system formed in an environment much like this, in the company of luminous stars that exploded and enriched our solar system with heavy elements as it was forming. The types of stars and ultimately planets that form in an environment like this depend on very complex interactions that play out over enormous scales in both time and space. Physical processes like gravity, turbulence, magnetic fields, radiation, and gas pressure are all important. And just as siblings might compete for things like food in the biological world, you might say that stars compete to gain mass. Words adopted from biology, like nature and nurture, work very well as metaphors for how stars and planets develop. So this is a much simplified version of what we've learned about how stars and planets form over the past few decades. To assemble this picture, we had to observe light at many different wavelengths and over many different scales. The first 3 stages pictured here are invisible and have to be studied with infrared and radio telescopes. Huge, cold, rotating clouds of gas and dust in space, about 1 trillion miles across, collapse through gravity to form stars surrounded by flattened structures we call protoplanetary disks, in which planets eventually form. The stages depicted here take place over enormous periods of time. So in order to assemble this picture, we've had to perform large statistical studies of many regions that are forming stars. And what we've learned, the bottom line, is that stars and planets form together, and we expect that most stars are accompanied by planets. One of the instruments that's currently providing a wealth of data on the composition and evolution of nascent planetary systems is the Atacama Large Millimeter Submillimeter Array, otherwise known as ALMA in Chile. These are high-resolution images of nearby, again the air quotes, protoplanetary disks that are enabling scientists to put together a picture of how planets form in these disks. ALMA is being used in joint projects with observatories that operate at different wavelengths, like the James Webb Space Telescope that we'll talk about in a bit, to give us a more complete picture of how stars and planets form. Now, just as we've been learning how stars and planets are born during the past few decades, using a variety of methods, we've discovered over 5,000 planet-sized worlds, otherwise known as exoplanets, orbiting other stars, stars that are not our sun. The method that's easiest to visualize is the transit method. So in a small fraction of cases, the orbits of stars take them across the face of their star, and you can actually record a small dip in the light output from the star during that so-called transit. And it's incredible how much information you can actually get about a planet in cases where you can observe a transit. Now, this graph shows basically shows some of the sizes of exoplanets versus their orbital period around their stars, which is kind of the same as saying their distance from their stars. So on the y-axis, we have size relative to the Earth, and on the x-axis, basically distance of the planet from the star. And you can see the wide variety of planets that we're discovering orbiting other stars, from very large planets that orbit close to their stars and are very hot, to rocky planets like our Earth, like like Mars, like the terrestrial planets. I also want to point out that in our solar system, there are no planets that span the size gap between the Earth and the planet Neptune that's considered an ice giant. And this is really interesting because there are a whole bunch of exoplanets being discovered that are so-called super Earths. Some of them may be rocky planets, others may be ocean worlds. And they're very interesting because, as I say, there's not an analog in our solar system. So this is a great, I think it's a great graphic of an artist's representation of a family vacation on a particularly interesting planetary system. One of the Earth-sized worlds in the star or orbiting a star known as TRAPPIST-1, where the planets are actually spaced so closely that they appear as huge moons in each other's skies. So here's a comparison of the TRAPPIST-1 system and the inner solar system of our solar system. The TRAPPIST-1 system contains the largest batch of roughly Earth-sized planets thus found outside of our solar system. And what's so remarkable about the system is that these worlds orbit in very close proximity around a very cool, one of those very cool red dwarf stars. Now, the green regions here around both the TRAPPIST-1 system and the inner solar system, that's the so-called Goldilocks or habitable zone, where the temperatures may be right, conducive to the presence of liquid water on a planet's surface. It's not really that simple, but closer to the star, temperatures are too hot. Further from the star, temperatures are too cold. Now, what I haven't shown you yet is basically how the TRAPPIST-1 system fits into the size of our solar system. Because the star is so cool, relatively speaking, the habitable zone is located very close to the star, but the entire system would fit well within the orbit of Mercury in our solar system. Now, just as the number of known exoplanets has grown, so does the number of potentially habitable exoplanets. Now, big caution here, potentially habitable doesn't imply inhabited or even necessarily habitable. It just means that these exoplanets are about the right sizes and distances from their stars that suggest temperatures may be right for the presence of liquid water, which is essential to all life on Earth. But we need to learn a lot more about these worlds to claim habitability and the presence of life. But with present and future observatories, we're getting there. So far, I've just been talking about stars and planets in our Milky Way galaxy. On a clear, dark, moonless autumn night, you can make out a smudge in the constellation of Andromeda. That smudge is the only galaxy beyond the Milky Way that you can see with your unaided eye from the Northern Hemisphere, although you won't see it like this. It's the largest galaxy in what we call the local group of galaxies. If you can spot the smudge, however, you might think about this. The Milky Way and Andromeda galaxies are approaching each other because of their mutual gravity, and in several billion years, they're expected to merge into a really huge galaxy. When galaxies merge, individual stars don't collide because, as big as they are, stars are tiny compared to the enormous distance between them. The Andromeda galaxy is about 2.5 million light years away. I want to point out that this is still, the light from this galaxy still comes to us from only 1.5 hours before midnight on December 31st on the cosmic calendar, but before anatomically modern humans arose on the Earth. Stepping out further into the universe, we see that galaxies come in many varieties, like the beautiful examples you see here. At tens of millions of light years away, the Hubble Space Telescope was still able to make out many details, and the shapes of galaxies can tell us a lot about a galaxy's history. For example, the antenna galaxies are an example of merging galaxies. Now, if you're listening to me earlier, even though the universe is expanding on large scales, on smaller scales, gravity actually dominates. So galaxies and clusters can actually merge because of their mutual gravity. And as they merge, cold interstellar clouds can get compressed, resulting in a lot of star formation. So that's what you're seeing here in those fuzzy pink patches, which are hot hydrogen gas lit up by luminous young stars. You can also see some examples here, a lot of examples in the Whirlpool galaxy. So these are extragalactic examples of stellar nurseries like the Orion Nebula in our galaxy. Now we're still in late December on the cosmic calendar. Over the years, the Hubble Space Telescope took several deep views into our universe by collecting light over the course of days or weeks from seemingly empty patches of sky away from the plane of our galaxy. There are nearly 10,000 galaxies in this image, which is only about 1/10 the diameter of a full moon. The brightest and most defined of these galaxies are at a distance of about 1 billion light years, and the smallest and reddest are at distances about 13 billion light years, corresponding to a time when the universe was only about 800 million years old. So we're spanning most of the cosmic calendar. We can go out to even larger fields of view, and the Hubble legacy field is comparable to the size of the full moon. In the legacy field, there are about 265,000 galaxies, stretching back in time 13.3 or so billion years. Just about every point of light, with very few exceptions, just about every point of light is an entire galaxy, not a star. And in this image, light from some of these objects comes to us from a time when the universe was just about 500 million years old. In the part of the universe we can observe, there are hundreds of billions of galaxies. With approximately 100 billion stars per galaxy, that comes out to roughly 10 million quadrillion stars in the observable universe, which is a 1 followed by 22 zeros. And we have good reasons to think that there are even more planets than stars. In our galaxy alone, we estimate there are more than 20 planets for every person who's ever lived. This chart compares how far back in time some different telescopes and instruments can probe. The James Webb Space Telescope, which is no longer in the future, it was launched a bit over a year ago, is filling an important gap in observations by beginning to probe the era when the first stars began to form. JWST is a much bigger telescope than the Hubble Space Telescope, so it can collect fainter light, but it also operates in the infrared. And because of the expansion of the universe, the light from very distant galaxies is Doppler shifted into the infrared because they're receding from us so fast. So you're familiar with the Doppler shift as regards sound. Similar to sound waves, light waves get compressed to shorter wavelengths or stretched to longer wavelengths, depending upon whether a source is approaching or receding from us. Now, in the case of very distant galaxies, all are receding due to the expansion of the universe, and their light is shifted to longer wavelengths. The more distant the galaxy, the faster it appears to be moving away from us. These are examples of what we call emission lines in the infrared spectra of 4 galaxies in this field of galaxies that was observed by JWST. And they illustrate how spectral lines of different elements are shifted to longer wavelengths as you go out to more and more distant galaxies. Now, in addition to contributing to our understanding of the early universe and how the first stars and galaxies formed, JWST will help us understand important details about how planetary systems form, which will help us better understand the diversity of the exoplanets we're discovering. JWST will also study the composition of the atmospheres of some exoplanets, searching for combinations of molecules that can serve as important biomarkers indicating a planet's habitability. The TRAPPIST-1 system is a high priority target. Now, this is an actual spectrum of an Earth-like planet, but it shows some of the important molecules can, in principle, be detected using a technique called transmission spectroscopy, where an exoplanet's atmosphere absorbs light coming from its star at specific wavelengths corresponding to different types of molecules. As the exoplanet transits in front of its star, its atmosphere can absorb light from that star. So in this spectrum, you see there are molecules like water, methane, ozone, carbon dioxide, all present in the hypothetical exoplanet's atmosphere. Determining conditions for habitability on exoplanets is an important next step in searching for life beyond Earth. So if your mind hasn't been expanded enough by now, in a recent webinar sponsored by the Institution on Religion in an Age of Science, physicist Marcelo Gleiser said that the paradox of knowing is that it creates more not knowing. And he pointed out that as the island of our knowledge grows, so do the shores of our ignorance. Or as I've heard most of my life, the more we know, the more we realize we don't know. And that should keep us all humble. Thus far, we've been talking about normal matter, labeled atoms, in this pie chart. Less than 5% of the universe is made up of atoms. Dark matter and dark energy are 20th century discoveries whose presence is inferred by their interaction with known things. Dark matter is matter that doesn't interact with light in any way, shape, or form, but its presence can be inferred through its gravity. Fritz Zwicky and Vera Rubin were pioneers in studying dark matter. Zwicky demonstrated that the gravity in clusters of galaxies was greater than what could be accounted for by the visible matter. And Rubin found that stars in the outer reaches of galaxies orbited the centers of galaxies much faster than could be explained by the distribution of normal matter. The Large Synoptic Survey Telescope, currently under construction in Chile, was appropriately renamed the Vera C. Rubin Observatory. Dark energy, on the other hand, was discovered through precise measurements of distances to faraway galaxies using a type of supernova whose brightness can be accurately calibrated. These measurements showed that the expansion of the universe, which should be slowing down in time due to the effects of gravity, is actually speeding up. If this accelerated expansion continues into the distant future, other galaxies will be beyond the horizon of any hypothetical observers to see, and it won't be possible to piece together the universe's history as we can today. I like to say that dark matter and dark energy are what you might call known unknowns. We don't currently know what they are, but their presence explains many observable features of the universe. And of course, it begs the question, what unknown unknowns might be lurking around the next corner? And by that, I mean, there may be things out there that aren't interacting with anything that we haven't discovered yet. So I'd like to, in the remaining time, I'd like to share some reflections and resources that I hope will be helpful to the seminary students and others involved in science and theology discussions. I've known various members of the Vatican Observatory since I began grad school at the University of Arizona more than 40 years ago, and they've had a profound impact on the way I personally relate science and religion. Father George Coyne distinguished between faith, religion, and theology. He noted that religion really refers to the practices of one's faith, and theology, at least in the context of theistic traditions, refers to faith-seeking understanding. So just as science seeks to understand the natural world, theology seeks to understand one's faith. The Vatican Observatory recently put Father Coyne's personal manifesto online. However, George emailed it to me over 20 years ago when I was attempting to articulate some of my own views. I'd recommend it. It's a very short read. I would also recommend this very new book by the Vatican Observatory, Scientific Perspectives in Fundamental Theology. It's not a short read. One quote from Father Coyne's personal manifesto I'd like to read is, "If I believe that the God of faith is also the creator of the universe, my scientific knowledge of nature, cleansed of its imperfections, can provide me a glimpse of what God must be like." So first of all, science can't prove or disprove God. However, it can and does influence the way people who believe in God think about God. So what are some things we can say about the nature of the universe? Well, the universe is creative, interactive, and relational. George Coyne saw the universe as the product of a loving rather than a designing God who imbued creation with a measure of its creator's creativity. And similarly, Lutheran theologian Phil Hefner has developed this idea of humans as created co-creators, knowing that creativity is an essential part of our human nature. Now, Phil Hefner is a name that should be recognized by everyone associated with the Lutheran School of Theology, and he's another person to whom I owe a debt of gratitude. Not long after my family and I moved to Chicagoland in 1998, I began exchanging emails with Phil, asking him all sorts of theological questions, and he never failed to respond with thoughtful, extended replies. I'm happy to announce that this recent book, Human Becoming in an Age of Science, Technology, and Faith, honors the career of Phil Hefner and contains contributions by several prominent theologians and philosophers who reflect on the creativity of nature, of human beings, and God from different perspectives. Similarly, Interactive World, Interactive God brings together scientists, theologians, and philosophers who reflect on this emerging picture of an interactive and relational universe, and what that might be to ways we think about God. There are also some wonderful presentations on the website of IRAS on this and other themes. There's a recent webinar by Jeremy Lent entitled "Weaving a Web of Meaning, how recognizing our deep interrelatedness lays a path to sustainable flourishing." So another observation about the universe is it's vast in space and time. Okay, so that's a rather obvious statement. But I think it's important to acknowledge that as we learn more, the universe has only gotten bigger. It's never gotten any smaller. Most of the universe will remain forever inaccessible to us. If we do discover life nearby, again, the air quotes, the universe must be teeming with life. However, not discovering it doesn't mean it's not there. So for those who affirm that the God of faith is the creator of the universe, this is a humbling reminder not to put God in a box. And I want to note that a vast cosmos need not imply an impersonal God, and there is nowhere near time to unpack that statement. But I do highly recommend Brother Guy Consolmagno's Casiris presentation, "Your God is Too Small." And you'll have access to this. This is being recorded. You'll have access to these references later on. So Christianity has been accused sometimes of being an anthropocentric religion. But there are many texts in scriptures, both in the Hebrew scriptures and the Christian scriptures, that kind of turn this on its head. In the Hebrew scriptures, you will find lots of great material in Psalms and in Job. And in the Christian scriptures, John, Ephesians put Christ in a more cosmic kind of a context. Science actually doesn't solve mysteries, it deepens mystery. And if you want to look for some great ways of relating religion and science by evoking the response of awe and wonder that both we get in our religious reflections and also our scientific understandings, Reverend Bruce Booher maintains a website called mysteryandawe.com, which has wonderful resources. Bruce is a retired ELCA minister who started his career majoring in physics at MIT. One of the resources on that website is a book called Dangerous Wonder by Michael Yaconelli, who's a writer, theologian, church leader, and satirist, who expresses the view that the most critical issue facing Christianity today is dullness. He says, we have lost our astonishment. He goes on to say that the church should be full of Christians who see questions rather than answers, mystery instead of solutions, wonder instead of explanations. And similar thoughts are expressed in this quote by Jewish scholar Abraham Joshua Heschel and by Pope Francis. So the real possibility of discovering extraterrestrial life, as well as the likelihood of having a human presence on Mars within the next couple of decades, lend urgency to cross-cultural, religious, and ethical discussions. Lutheran theologian Ted Peters is one of the leaders in putting the contemporary space sciences, theology, and ethics into conversations on some of these topics. And Astrotheology is a book that examines some of the thinking about these issues, which I've also explored in this article, which you can find in Theology and Science, and in my chapter contribution to Intersections of Religion and Astronomy, which is a book that examines the ways in which cultural ideas about the heavens shape religious ideas and vice versa. If you're interested in astrobiology, but you don't want to read a tome, you might check out some of the archived monthly, very short articles I write on astrobiology, which can be found on the website of the Clergy Letter Project, which is an effort, it's an initiative to show that religion and science can be compatible. So finally, I want to say that science fiction is great at imagining what might be and exploring what should be. And I think science fiction presents a great unexplored opportunity to stimulate interdisciplinary dialogue. If I could scare up both the interest and funding, I would personally love to start an online reading club that would bring scientists, theologians, and philosophers together on a regular basis to discuss selected works of science fiction for the purpose not only of understanding each other better, but to stimulate new ideas through interactive conversations with the expectations that these discussions would lead to producing fruit that could reach a wider audience. So I'm coming very close to the end now. I do want to mention that the best way to learn about a community different from your own is to participate with them. Much excellent science and many new discoveries have come from people around the world participating in research along with scientists. Participation is a great way to learn more about the process of research and the professionals conducting the research. One of the recent projects on a popular platform known as Zooniverse is asking volunteers to help search for extraterrestrial civilizations. The URLs I've listed below here are links to an effort I led to engage faith communities in people-powered research, and one of many discoveries, well, a discovery in particular that enabled my current research. And if any of you happen to teach introductory astronomy and you'd like your students to participate in research using real data, we should talk. My email is at the beginning of this presentation. And I was going to show this, this little introduction to the Zooniverse, but I think I'm going to table that for now so we can get to questions. And I'm going to put up my last slide instead, since at least a fraction of you are present or future ministers, I want to end by inviting you to register for a webinar on March 25th that's being hosted by the Institute for Theological Encounter with Science and Technology. And it's presenting the Catholic Theological Union's Preaching with the Sciences project. This project was about seeking creative ways to incorporate science into sermons. And on CTU's website, you can find homilies that were developed through this project. You can also find a repository of sermons on religion and science that were developed by clergy representing diverse faith traditions on the website of the Clergy Letter Project. So again, you should be able to access these URLs after the fact. So I think what I'm going to do is exit right now and stop my screen sharing so we can take some, I've left a few minutes, I guess, Gail. We actually have till 7:45 for questions.
We have a 7:45. So
okay.
So first, Grace, let me thank you. I mean, what a fabulous tour de force. I mean, this was really amazing. Really enjoyed it. I'm opening it up for questions, and what I'd ask is, if you have a question, please raise your hand. I see applause coming from the audience as well, so that's really a good thing. And before anybody gets started, I guess I'll sort of start off and give people the chance to think about some questions. One of the things that's bothered me is the Arecibo site is closing. Grace, could you just talk a little bit about why that decision was made and what's taking its place?
It was, first of all, unfortunately, it was very badly damaged. And the decision was made that its heyday is past and it just wasn't worth the money to reinvest with all of the new observatories coming down the pike. And there are many present and future telescopes. So it is a loss. There are those of us who cry for Arecibo. As an undergraduate, I actually worked for a scientist who was doing radar studies of Saturn's rings using Arecibo. So, my heart goes out to all of that. As far as what's replacing it, I haven't personally heard of anything replacing it in Puerto Rico, but there are a number of new observatories being discovered, like across, or being developed, excuse me, it's a little late for me, that are being developed at all wavelengths. And there will be, if not a replacement for that particular telescope, there will be ways of investigating the sorts of things that Arecibo investigated. Thank you, Gail. Good question.
This is open for other people to ask questions. I'm kind of asking the students not to ask questions because I know they're going to have a little bit of time with Grace afterwards, but are there questions from the audience?
Everybody, I see a hand that went up.
Okay, yeah, Dan.
Yeah. Hi, Grace.
Hi, Dan. How you doing?
Yeah, maybe a technical question. You talked about, wow, there was a lot of stuff in here I didn't know, even though astronomy has been a hobby of mine. But one thing I'm curious about, the planets, the super Earths, the kind of planets we don't have in our solar system. Is it possible that the asteroid belt, there's, I guess, a missing planet there, either it never formed or something? Where that kind of planet would go?
That's a good question. Another possibility, you might have heard of Planet X or Planet 10 or whatever you want to call it. There's some evidence that there might be a large planet that's sort of in that category, way out beyond the orbit of Pluto. Now, obviously, that's not something that could harbor life. But the thing that we're discovering is that as planets are forming in these protoplanetary disks, initially there can be all sorts of different interactions due to gravity, due to viscosity in the disk. And that can really create all sorts of different kinds of planets. The other thing we don't have in our solar system is a so-called hot Jupiter. a huge planet that's orbiting, closer than Mercury to the sun. So it's the mass in the asteroid belt, I don't believe would put together. In fact, I'm pretty sure wouldn't create a super Earth. But the super Earths are really, really interesting because there's been a lot of modeling work done to suggest that those kind of worlds might have, and again, might, I have to underscore might, because we need observations to back up the models, but might include worlds that have large oceans on their surfaces. And in which case, those are worlds that could be very, very habitable. But again, in other systems. The closest ocean world, I'm not sure how close it is, but the TRAPPIST-1 system with the long string of Earth-like planets, that's about 40 light years away. So if there were life, if there were intelligent life on one of those worlds, or communicative life, a two-way conversation would be 80 years. So that also underscores some of the difficulty in thinking about, well, could we ever really communicate with extraterrestrial civilizations? So I've seen, I don't know if that, hopefully that more or less answered your question, Dan.
Yeah, kind of.
Yeah.
It's
Thank you. Yeah,
open-ended.
it is open-ended. It's open-ended. And if you're interested, I can keep you in the loop as we discover more information about these giant Earths, so to speak.
No, Grace, there's a question in the chat.
Yeah.
I was curious, this is from Greg Kaufman. I was curious what created your interest in the connection between science and theology.
Ooh, well, thank you, Greg. So I think, again, going back to my childhood and being so inspired by science fiction, I've always been interested in science, but also the questions that science is really good at raising, but it's not well equipped to answer. So science is really good at describing the behavior of things, at looking at, the how of the way things work in nature, in our universe. It's not so good at some of the meta-scientific questions, like why is there a universe to describe with mathematics in the first place? The most obvious thing that science can answer is can't deal with is itself. Why is it possible for us to do science? So there are all of these big, interesting questions that I've always been interested in, as well as the science. And I honestly think if I hadn't gone into a field of science, I might have actually studied theology. There are people like Al who have degrees in both. So my connection goes back a long ways. And I think science fiction inspires a lot of that imaginative thinking outside of the box, how we can maybe better relate some of these things. So thank you for asking that question, Greg. And of course, I was even more inspired when I went to graduate school at the University of Arizona, which is the part-time home of the Vatican Observatory. So that's where I met the Jesuit astronomers. And then I moved to Chicagoland to take a position at the Adler Planetarium. And lo and behold, the Zygon Center is here. So it was kind of a very wonderful piece of serendipity.
Thanks, Grace. There's a question from the Reverend Anders Nelson.
Oh, hi, Pastor Anders.
Hi, Grace. Good to see you. I wanted to ask a question. Yeah, go ahead.
By the way, I just wanted to say Anders is one of my pastors.
Oh, great.
Hi, Anders.
Yep. Wonderful to see you, Grace. Thank you so much for inviting me to join everybody here tonight. I had a question for those of us who are actively serving in congregations or are looking to serve in congregations in the future. Do you have tips for us to help equip those who we serve with this sense of curiosity? And I would imagine that some of the things that we're talking about tonight would relate with those things. How do we equip people to ask these good questions when they might come looking just for answers?
Boy, that, oh gosh, that's a great question. And I have to say that part of me feels that if we would have solved that, we would solve so many things, because curiosity just seems to be dead in so many people. And I suspect that a lot of it has to do with just the busyness of everyday lives, right? We're tuned into so many different things, we don't stop and look up. Thousands of years ago, people could look up and see thousands of stars in the night sky, and it was there. And now with light pollution in the environments, we can't do that. But we have these incredible images, both on the macro scale and on the small scale. And, I might suggest just running a slideshow, and I'd be happy to equip anyone with some beautiful, awe-inspiring slides and quotes that can at least get people to stop and think, wow, boy, look at the incredible cosmos that we're part of, that we live in. So let's talk. Let's talk more.
Great, thanks, Grace. Any other questions? There's a statement in here saying I'd love a copy of those slides. Certainly the video will be up on the website for anybody to kind of, flash through the slides if they want. We could probably do a PDF of the ones that you're allowed to put up as well, Grace, and put those on the website. Would that be a possibility?
Oh, absolutely. And I can, my email is, I showed at the beginning, gwolfchase@gmail.com, and it's G wolf like the animal, chase with no spaces or hyphens or anything like that. You can always email me, and I'd be glad to share things with you that way, or, extend some of these conversations further.
Thanks, Grace.
Sure.
I'm not seeing any other questions or comments.
If there are no further questions or comments, I could go back and share that Zooniverse video.
Why don't you do that? Why don't you do that, Grace? It'll, I think that'll be useful for everybody, and then we'll sort of end for the.
Okay, because this is really a great way to get involved in research, is to actually, let me share my screen again here. Okay, so I'm going to start this video. This is about a platform that everyone can use, regardless of your background, to become involved in research projects along with scientists and other researchers.
A brief introduction to the
Can you all hear?
The way we generate knowledge.
Yes, we hear it.
The last century. Technological advances are creating huge amounts of data that can be hard for researchers to handle by themselves. The Zooniverse is an online platform that connects these struggling researchers with people all around the world who want to help. Together, these volunteers have contributed to many incredible discoveries and a huge amount of wonderful science, such as helping to sift through 1 million images of galaxies in the first project, Galaxy Zoo. Not only did this help to create the most comprehensive survey of galaxies, having so many eyes look at each single data point led to many unexpected discoveries, including a new class of galaxy that appeared as small green blobs, or as the volunteers called them, peas. The Zooniverse has since grown to include over 150 different research projects across all sorts of subject areas and scales, from the stellar to the subcellular and everything else in between. All of this is possible because of a community of nearly 2 million volunteers around the globe, who together are changing the way that modern research is done. Why don't you explore the Zooniverse today?
Oops.
Great. Thanks, Grace. That was really cute. Nice video.
Yeah. So, I invite anybody who's interested in almost any topic of research to check out Zooniverse.org, and there's something for everybody there.
Okay, let's thank our speaker one more time. If I see clapping online, and Grace, it was really great, really perfect. What I think we should do is end the webinar for everybody in the group. Let all the class students and Grace take a 10-minute break, and then we'll come back at 10 minutes till and give the students a chance to ask some questions of Grace. Okay?
Great,
So-
thanks, Gail.
And thanks everybody for joining us this evening.